yesterday, and so my preparation was maybe not complete. And I first of all I'd like to apologize. My talk will be finished before 1 hour. So. What I want to discuss in this talk is arithmetic and topological analogy of classical Dan-Nielsen isomorphism. So first I would like to discuss topological motivation. Then next I would like to review some known results and unknown results. In the last part, I'd like to present very small remarks, new remarks. Okay, so topological motivation is classical Dan-Nielsen isomorphism. Which is known as a mapping class group, MGN, is isomorphic to outer automorphism group of fundamental group of punctured Riemann surface. So mapping class group is, I don't want to define here, but G and N means the surface of genus G and N punctures.
Did you write MGN or gamma G?
MGN? Oh.
MGN is the modulus.
Yeah. No, this is group. So this is the pi zero of differ of this one. Yeah. And outer automorphism, I should restrict to some special classes of outer automorphism group. The pi gn means the pi 1 of punctured Riemann surface. So we have natural generators relations and well-known relations. And this restriction respects orientation of this surface together with the conjugacy classes of each loops around the punctures. Then classical Dan-Nielsen theorem implies
so the product is in skips of 2.
No. From 1 to n.
No, but the first product.
First product, I to G plus I. So.
Oh, I and G plus I.
I and G plus I. Yeah. And today I want to view this map. I like this rho Dan-Nielsen map, rho dn as representation of mapping class group in simpler group IGN. And motivation is this is a difficult group, and this is a much easier group. And so the main motivation is to study this difficult group by representing it in the outer automorphism group of simpler groups. And but so I want to introduce graded Lie versions of Dent-Nielsen map by using the weight filtration of this fundamental group. So weight filtration is I like just the whole group just by for simplicity pi. Then we have some central descending series. But weight means basically we want to attach these generators as weight 1 and these generators as weight 2. So by definition, the first filtration is commutator subgroup plus adding all Caspidal loops. Then after that, I take central filtration. So then this is usually lower central filtration is rapidly decrease than weight filtration because of the existence of these things. So only when n equals 0 and 1, this weight filtration coincides with the lower central filtration. Yes, n minus 1, yes. Thank you. And then this weight filtration induces.
Is this equivalent to studying some sort of a pure version of the mapping class where you are? Where you look only at automorphisms that preserve the homology or something like that?
Yeah, after that I will introduce these Taylor groups and so on. But first of all, in this level, I allow all automorphisms, also permuting punctures also allowed. Okay. Then the weight filtration of this fundamental group induces weight filtration of mapping class group in the following way. K is sigma such that the difference of the image and the pre-image is inside K plus I for any x in I and any I. And also, this modulo some inner automorphism. So modulo inner automorphism group of the case part of PyGN.
So in the following MGN
Yeah.
You're assuming that the automorphism preserves the. How do you know those are characteristic subgroups? Isn't that an extra condition that the automorphism preserves the weight?
Characteristic subgroup of pi?
Yes, why is pi 1 characteristic? It doesn't look it.
No, pi 1 is not characteristic. Yeah, it's
So-
a specific subgroup of
So
D. Yeah.
why is the group of automorphisms always equal to mgn0? Because you would read that phi of x was also.
In the case of 0, 0 is by definition.
Then in a lower
The
one.
out plus is extra conditions. It's not all automorphisms. It's only ones that preserve z up to conjugacy.
Yeah.
And it is characteristic for that type.
Oh, so it's out plus of.
Yeah. So yes.
Yeah.
Oh, I'm sorry. So I assumed this. I think this.
Wonderful.
There are some missing points in my preparation. And normally, MGN1 is called Torre subgroup. And the first question is isomorphic to symplectic group and symmetric group of degree n, and that these are acting on the homology of compactified Riemann surface, and this part acting by permutation and points. Then from this induced field version, we have a Lie version of that is the embedding of graded pieces of MGN k equals 1 to infinity into the graded pieces or derivation case derivation special derivations of this graded Lie. This I don't want to give explicit definition, but special derivation or outer derivation, which is respects the structures of punctures of this Lie algebra, and degree k means the shift weights from I to I plus k. Okay. And this embedding also easily verified to preserve the action of this the first pieces. So this is simply with times Sm equivariant embedding. But this is our main target to study in this talk. And although topological Denisohn map is isomorphic, but this Lie version is known as not isomorphic. So inversion is not isomorphic. And but the target, what we want to know is the exact structure of this topological ingredients, and this the target space is very concrete definitions of simpler Lie algebra derivations of simpler derivations. So one can compute explicitly of which kind of irreducible representation, for example, symplectic group and Sn, Frobenius characteristic of Young reparameterizations of Young diagrams, pairs of Young diagrams appears decompositions. And how many boxes of each irreducible components of this group appears is easily computed. But this part is rather mysterious Lie algebra. Only known is Rich Hayne proved in 1997. This is almost quadratic Lie algebra. Generated by the degree 1 and quadratic if G and N is not very special cases. Okay. So, but now today I want to focus on how much this Lie version of Dehn-Nielsen map is far from isomorphism. So, some known results on non-isomorphic results. Lie versions. In fact, the following components in appears in co-kernel of Dehn-Nielsen map as multiplicity free. The first example is Morita's trace components discovered in 1993, which is 2k plus 1 of SP. 2k plus 1 means Young diagrams of horizontal boxes, which is just the symmetric tensor product of 2k plus 1 and homology of Riemann surface. And this component appears in special derivation of 2k plus 1 of pi in multiplicity free, and Morita proved this is not inside the image of this topological inclusions. second example is proved by Matsumoto and at almost the same time some joint paper with Gao Ueno in 1996. And there is a fixed part of a symplectic group in plus 2. But I should have to say this multiplicity-free condition is only for 1 and 3, and for the second obstructions, multiplicity is much bigger than 1. So, which appears 4k plus 2 of special derivations, and k equal 1, 2, 3. So 6, 10, 14, and so on. And the third one, it is also multiplicity-free obstruction with Enomoto Sato established in 2 years ago, where they found alternating tensor product. This appears in special derivations of degree 4k plus 1, which is also in the co-kernel of the Nielsen map in Lie version. So I would like to add some remarks on these results. But before that, there should be many other co-kernels. But still, the explicit description is available only for these 3 types. For remark on 1 and 3, and their proof of Morita and Enomoto Sato is given by explicit computation on combinatorial group theory or free Lie algebra and or Magnus expansions of such thing. But they didn't give a topological meaning of these special obstructions. But recently, topological meaning is in progress very rapidly by the research of Kuno Kawazumi on the Mashu slide. So I hope in coming few years they will provide very clear pictures on this first and third obstruction to be versions of Danielson map. And for the second one, here this is called Galois obstructions. From GQ, which should be better mentioned a little bit because of the title of my talk. So for this, we have a very arithmetic meaning of these obstructions. Namely, one can extend Danielson map to arithmetic monodromy. Coming from universal family of punctured curves over moduli stack of genus G and endpoint punctures over Q. Namely, one can extend the MGN as a profinite completion, and then MGN can be extended. Profinite completion is just inverse limit of finite quotients of these discrete groups, but we can extend it to one of MGN over Q, and whose quotient is GQ. So extension. And then this group is a bigger group of mapping class groups, which acts naturally on outer automorphism of Royal completion of the fundamental group of Riemann surface. Then for this group is almost similar generators and relations with the classical fundamental group. So we can introduce similarly weight filtration in this fundamental group, and then we have erratic version of Danielson map. And also its Lie algebra version from graded pieces of I1 MGN into the pieces of special derivation of L. Yeah. And here inside we have classical graded pieces from mapping class. And the gap, this gap is coming from Galois group over Q.
Excuse me,
Sorry?
I missed what is capital MGN?
Capital MGN. Yeah, I'm sorry. So this is moduli stack.
Capital CGN?
Smooth.
take the covering, take an entire finite entire covering and go to the no? Oh, can you do it?
Capital, this one.
Yes.
Yeah. And then you can take étale fundamental group of this thing over Q. So I don't explain the details, but there is such object which contains a topological mapping class group as a normal subgroup, and the quotient is the same as a Galois group over Q. This gap is very huge. And the theorem in 1996 is this I call Galois gap. Galois gap is independent of genus and number of punctures. This is somehow Lego coming from Lego structures of modular space of curves. Then one can apply this to very special case of genus 0 and punctures, 3 punctures. Then M03 is 1 point. And pi 03 is pi 1 of 3 punctured sphere is free group of rank 2 and pi 1 M03 is just GQ. Then we have this elladic representation can be found coincide with the basic, very basic representations studied by Belli, Ihara. And also you have you may take L completion of this thing. Then it is a very famous story which factors elladic Galois-Teichmueller group. Then you have this elladic Galois-Teichmueller group in which in big part you have a motivic part, and also you have Sule characters. Okay, so this gives weight 4k plus 2 obstruction. Which was introduced in second part. But of course this just the elladic avatar of zeta values at odd degree. So this is just elladic version of zeta values. So taking Lie brackets of such things will produce more obstructions corresponding to multiple zeta values. Brackets. More. Multiple zeta values. But which will be discussed in other talks. Okay. So perhaps I would like to go very quickly these computations a little bit. Some very small complications, extra obstructions. First one is concerning the stable derivation result. This direction, I want to consider not only universal family of punctured curves, but over moduli stack of over Q. But also, I want to consider configuration space family over modular space. Then, which is the in fiber-wise you take products of punctured curves minus all diagonals. Minus. Okay. Then we have Dan-Nielsen map from pi 1 MGM to outer automorphism of pi 1 of this configuration space. So I just write bracket R to the bracket R means the configuration pi 1 of configuration space. Then, but I take also some restrictions respecting the projection, natural projections of this fundamental group to forgetting one direct component of a direct product. Then one can form naturally such sequence, and finally it goes to the original Dan-Nielsen map. So this is a natural map considering configuration space. Then Ihara and many others proved this sequence is injective. And recently Hoshi and Mochizuki finalize this injectivity results. Then one may consider Lie versions of this map. But okay, so but you know the arrow is in this way, so one can factor the original Dan-Nielsen map to be all such configuration versions. So okay, but this is injective. So actually, it factors through the all special derivations of configuration space. But in this time, this S means not only special, but also symmetrized concerning the permutations of direct product of this geometry. So one can form stable parts of original things. Yeah. So I'm sorry. Maybe I should put somewhere. And actually, Ihara proved that this intersections stops at least R is at 2 or 3. So and this infinity can be replaced by. So in the case of genus 0 and genus puncture 3 case, it can be 2 if 3 if G equal 1. This is result of Ihara and this is result of Tsunogai. And but in this, and then Ihara also proved this inclusion is not equal. So there is a gap between the target of special derivation with stable derivations of this configuration version. So and this gap is actually comes from pentagon relations of Galois-Teichmueller group. But in the genus bigger than 1 case, Tsunogai's case, we don't have non-gaps between this thing. But if you find the gaps between these two spaces, then it is obviously the obstructions to reversions of original Danielson map. A small remark is fact. So obstructions of Moritas and Galois are stable. Namely, these two kind of obstructions doesn't detect the gaps between. But for question is how about Enomoto-Sato case? This is still unknown. And finally, another little observation. Just considering the genus 0 case. Genus 0 case. Our main target is reversions of Danielson map, but here we have genus 0 moduli mapping class group. It is essentially the sphere braid groups modular torsion, little torsion. And here we have special derivations of eyes of n. And So since the genus is 0, so it is representation space of both representation space of symmetric group of Sn. And as I mentioned, this target space is easy to compute because it is a very explicit linear space of derivations. But also in the genus 0 case, this can also computed as a Frobenius characteristic in representation ring of Sn. By using Getzler's series of Euler-Poincare or cohomological components in Sn. And just converting this his generating functions in symmetric functions to by using Möbius functions, and then one can compute this space as a representation of Sn. And then my observation is so this type of Young diagrams. So n minus k and k. It appears in 0n. Appears in cokernel of Denius map, multiplicity free. But my computation is limited by the capacity of my personal computer, so unfortunately this is only 3 degrees. So, but it seems one can compute a little more by
you mean that it's
using
inside S there, or not inside? And
in cokernel.
yes, but it lies inside where?
Sorry. Yes. I'm sorry. So yes. You are right. Of course. So degree. No, what's this? Thank you very much. But of course, in this case, we consider stable situation. So n should be bigger than. Okay. And if n is smaller than 3, then we have to specialize all these computations by classical representation theory. So my conjecture is perhaps this kind of obstructions appears in all odd k. But I don't know what is the geometric meaning of these obstructions. But this kind of Young diagrams appears as irreducible representations of temporary loop algebra, if one can consider the deformation of this Danielson map, then hopefully there should be theoretical interpretations of such. But it's more future subject. So, thank you very much.
Thank you. Is there any question? I have one.
So usually people who work with operas, usually when they see a family of representation of the symmetry group, the first idea is to consider all of them and then to see if on this collection whether or not they have a structure of opera on this family. So for instance, by Getzler results, for instance, we know that, well, let's say the homology of M0n, consider all of them, yes, this forms an opérage. What about, have you seen any result of this shape for S there? So if you take S there, you say that this representation, the special derivations, yes.
Yeah.
You say these are representations of the symmetry group which are easy to compute.
Yeah.
Right.
Yeah.
Is there any operade structure here or?
Operas are, well, actually, I just started learning about operas in your book. But, yeah, but
Do you see that could help to organize this embedding? When you take the full collection of n there, a full collection of n here, then when maybe we have an operade in the category of Lie algebras with the sum. So that's it's a symmetric monoidal category. So maybe this can be, we can have richer structure here, not only just maps for fixed n embeddings of Lie algebras, but maybe.
Isn't graded K M0n the causal dual of the cohomology of M0n?
yeah,
Yeah, and so the common of M0n
quadratic
is by Getzler.
Yes.
Yeah, so there you have the structure.
But this is for the left-hand
left.
side, yes, not
Yeah.
the right. Yeah. For the left-hand side, yes, but for the right-hand side, and then to see this Getzler algebra operas embedding into this guy on the right-hand side. So.
Yeah, so Getzler computed such thing in genus 0 and genus 1.
Yes.
But for general G, I don't know. Do you?
No.
Maybe.
No, but the point is that maybe one could phrase theorems which could say something like, you know that this is an embedding. So we have an operatic structure on the left-hand side. Let's say we have one on the right-hand side. And then you have maybe a morphism of operas, and then the co-kernel inherits some algebraic structure. So operatic algebraic structure. So that might help to organize. That's the role of operas. Organize, put more algebraic structures so that we can have a better understanding.
So yeah, as an undergraduate, I did some calculations on this graded M0n, and I don't remember the details very well, I'm afraid, but I seem to remember you could write it as some stable Schur functors acting on standard representations, and I think you could prove that the alternating representation never exists, for example. Does that sound
Alternating representation. Really?
Using results of Reutenauer in the last chapter of his 3D algebras, he has a very difficult theorem. Apply that to this.
Okay, let's see. Yeah. I have a table of representation, but up to k equal 7. So let's check. Yeah, your suggestion.
Any other question?
Could you say a little more about what was on the fact that from Lie brackets you could get information on the what is on the right, some more details on that?
No, here.
Here?
We used to have more details.
For here?
Yeah.
Yeah. This for this. Lie bracket is in the derivations. You have abstractions corresponding to single zeta function. But if you take more Lie bracket in as a derivation, then it should be more. It should give rise to more abstractions. And normally it corresponds to multiple zeta values. But for this, yeah, there is no. I didn't give detailed explanations. Yeah, but maybe other person talk will give better explanations.
Any other question? Okay, thank you again.